In this lecture, we'll start to consider the properties of stars. Since stars, of course, are the energy source for biology and the fuel for astrobiology, but we need to consider their particular properties and their evolution, as well as the way they've made their heavy elements. Let's get a sense of the size of the stars compared to the planets. There's the Earth. Receding from view, we see Jupiter, the largest planet in the solar system. As we shrink back, the Sun comes into view, and the smallest red dwarf star to its left. Proxima Centauri, also a red dwarf. And here the Sun. Jupiter 10 times smaller, the Earth 100 times smaller. There are stars smaller than the Sun, as you've seen, red dwarfs, but there are also stars much larger, stars whose luminosity is huge, whose lifetimes are short. Some of these are the brightest stars in the night sky, visible to the naked eye, like Arcturus. Some of them are red and blue supergiants with enormous fusion reactions going on inside that are creating heavy elements, even as we speak. Also see the names, some taken from Greek mythology, some are Arab words, representing the fact that the Arabian astronomers named many of the brightest stars in the sky. Here, the red giant Antares. Red giant is the fate of our sun when its lifetime is over. And still, with the sun receded from view so that we almost can't see it, we're not at the size of the largest stars. The attribute of stars that astronomers key in is their spectral type, because stars were first classified by measuring spectra of them and looking at their colors. These two properties, the surface temperature or color of a star, with blue representing hotter and red representing cooler, and spectral type, which is an indication of the chemical composition and also the energetic state of those atoms in the surface of the star, are used to classify stars uniquely. This work was done first in the 1930s by Hertzsprung-Russell, and the diagram astronomers use to classify stars is called the Hertzsprung-Russell Diagram. It's essentially a graph of surface temperature against luminosity. And in the spectrum of star types, the Sun is not exactly typical, which is to say average, but it's in the middle of the range. So the Sun is a yellowish star with a surface temperature of 57 or 5800 Kelvin. And there are stars much less massive than the Sun, at the left there, an M-dwarf star, near the fusion limit of about 8% the mass of the Sun. And these stars are quite cool and red. Going in the other direction, we have stars more massive than the Sun, and these stars are pumping out enormous amounts of radiation. So their equilibrium state leads them to very large physical sizes. And the most massive stars are O and B stars, such as the hot young stars you'll see in star formation regions in the night sky. They are the hottest, the most massive, and also the most luminous. The determinant of a star's life and all of its properties is its mass. Massive objects have a strong gravitational influence, and their self-gravity essentially creates very high temperatures and pressures in the interior. As we've seen, these very high temperatures and pressures can fuse heavy elements and so generate the periodic table's worth of elements, including life's essential ingredients. Lower mass stars have smaller self-gravity and thus lower central temperatures and pressures. The fusion limit of 8% the mass of the Sun corresponds to a configuration where the central temperature and pressure never exceed 5 or 6 million Kelvin, where the feeblest kind of deuterium fusion is possible. At 10 million Kelvin, hydrogen can fuse into helium, as is happening in the Sun. So a substellar object, or an object no longer shining by its own light, is one that is too cool for fusion to occur in any manner. At the upper end of stars, stars more massive than the Sun, extremely strong self-gravity creates extremely high temperatures and pressures. Those conditions obviously can lead to the creation of heavy elements. The other thing that happens is that stars at the high end of the mass range evolve or live their lives much more rapidly than stars at the low end of the range. The reason stars don't collapse to a point, or the reason they have physical size at all, is because of the fusion reactions in their cores. Anything called a main sequence star is a star like the Sun, but could be of different masses, that is converting hydrogen into helium by the fusion process. Fusion, of course, releases energy, and the energy release creates pressure. And that pressure acts in opposition to gravity. And if that equilibrium between gravity pulling inwards and the pressure due to fusion reactions pushing outwards, that gives a star its particular size, and is the reason why stars don't collapse and have a large physical size. We've seen that the fusion process is combining small or light atoms into heavier atoms sequentially. This is an example of the process that occurs in the sun. A proton-proton chain, which in 3 stages goes from hydrogen to helium. The protons that are part of this process are left over to indulge in nuclear reactions in the future, and so are recycled in a sense. And the sun is gradually building up helium in its core. It will do this at a steady rate, more or less, for another 5 billion years, having done it for about 5 billion years. The fusion rate, or the rate at which a star is converting light elements into heavier elements, is the thing that tells us how fast a star consumes its available fuel. So given the size of the fuel tank, the mass of the star, and the rate of nuclear reactions, the rate at which it's burning its fuel, we can calculate, or at least estimate, the lifetime of a star. So fusion rate, as we've seen, depends on the conditions in the core. The additional mass compresses the core, so these are very high density regions, and that high density in and of itself facilitates the nuclear reactions, because they're based on collisions between particles that are positively charged, protons or other nuclei, and that do not want to be in the same space. So the temperature and pressure is overcoming electrical repulsion as a microscopic force. So with that stronger compression and higher core temperature, massive stars are achieving much faster fusion rates than low-mass stars. So the lifetime depends on the fusion rate, and we can use the analogy of fuel tanks and imagine 2 cars, one that's fairly fuel efficient and one that's fuel inefficient. The blue car, the efficient car, consumes fuel at a rate of 10 gallons per hour, and the red car consumes fuel at a rate of 1 gallon per hour. If each car had the same size fuel tank, the blue car will only last or live or travel for 1 hour on the road, or a 10th amount of time as the red car. So this is the basic of the calculation, but the other thing is the size of the fuel tank. The more massive stars are massive, and since their mass is their fuel, they have bigger fuel tanks. But it turns out that the rate of evolution of a massive star is so rapid that even though their fuel tanks are larger, because they're more massive, they live shorter lives. And so when the calculation is done properly, making a model of the stars, the high mass stars in the universe, in our galaxy, are the blue cars in the analogy. And their fusion rate is very fast, and they have very short lifetimes. So it turns out that a massive star, about 10 or 20 times the mass of the sun, although it has a larger fuel tank, lives far shorter than the sun. The sun has a total lifetime of about 10 billion years. A star 10 times the mass of the sun has a lifetime of 10 or 20 million years, 100 times smaller, despite the 10 times larger fuel tank. So obviously the math suggests that it's using its fuel or fusing or creating energy at 1,000 times the rate. At the other extreme, there are stars with 10% of the mass of the sun, the red dwarfs. Their fuel tanks are 10 times smaller. But their fusion rate is so slow that they can last for 1 trillion years. That's 100 times the lifetime of the sun. So despite a 10 times smaller fuel tank, they're living 100 times the length of the sun. So once again, their fusion rate is 1,000 times less than the sun. So we have this enormous range in the stellar spectrum of masses. From the most massive stars to the least massive stars, it's a factor of more than 1 million in the rate of fusion or energy production, and a correspondingly large factor in lifetime. Here are the examples of lifetimes for particular spectral type of stars. So these are based on particular models of stellar evolution rather than the round numbers I was just giving. So the G-type star, which is the sun, is 10 billion years, and we're halfway through that lifetime. An F-type star, somewhat hotter star than the Sun, not actually blue, but pale pink if you could see it in the sky, lives for about 3 billion years. The M dwarfs live for 1 trillion years, eking out their energy at a very low fusion rate. How does this relate to biology? It relates to biology because the Earth has had life for about 4 billion years. It took 1 billion or more years for that life to be complex. So if we think that it takes a while either for life to get started or to get to a complex and potentially interesting state, then we need a star that lives a sufficient length of time, and this may be the minimum. So stars more massive than an F star, living with shorter lives than 3 billion years, may not be as interesting for astrobiology. At the other extreme, there's plenty of time available, and there are plenty of stars. So the M dwarfs, the red dwarfs, have enormous lifetimes of stable fusion reactions and energy production. So on the surface of a planet, the radiation will be available for enormous spans of time, potentially allowing interesting things biologically to happen on the surfaces of those planets. So there is a sweet spot. We can call it a Goldilocks zone, much like the Goldilocks zone of the habitable zone, that the most massive stars are probably too massive to host life simply because their lifetimes are too short. The fate of life on a planet around a massive star is the violent destruction of that biosphere by the supernova explosion that ends the star's life. It is very unlikely to imagine biology surviving a supernova explosion of a massive nearby star. At the other end of the range, the low-mass spectral types have very long lifetimes and stable energy sources, and so they represent good and interesting real estate for biology in the universe. We think, although we don't know, that long-term stability, by which I mean stability over hundreds of millions or even billions of years, is necessary for the emergence of complex life. We can search for habitable planets now using this extra information because we want to look for the right spectral types of stars. And Kepler did this, for example. Kepler, as we know, was staring at over 150,000 stars in a small patch of sky. But not all of those stars were equally interesting, because many of those stars were too massive to be hosting potential life because of their short lifetimes. So Kepler used a selection to make sure it was only looking at the most interesting stars. Since most stars are low-mass stars, that doesn't actually exclude very many. How many favorable host stars are there in the Milky Way? Well, our galaxy is constantly forming new stars. And the best estimate of that star formation rate is that there are about 7 new stars per year in the Milky Way in the sweet spot, or the range of mass and lifetime suitable for the hosting of life. That's not very many as a number per year, but averaged over hundreds of millions of years, it's billions of new sites for life on interesting time scales. So we've seen that stellar properties matter for the existence of life, because the host star has to live a suitable amount of time and produce a suitable amount of energy for biology to exist. Stars are classified by their spectral type, which is an indicator of their mass. And the lifetime of a star is completely determined by its mass. Stars much more than 2 or 3 times the mass of the Sun have lifetimes that are probably too short for complex forms of biology to exist on their surrounding planets, which is to say they live less than a few billion years. However, low-mass stars, the most abundant type of star in the galaxy and in the universe, have very long lifetimes, hundreds of times the lifetime of the Sun as a main sequence star, and so they represent excellent and abundant real estate for the possibility of astrobiology.